Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture we will be looking at diffusion models. Just as a recap of what we have done in the last couple of lectures, so we looked at transfer learning as a strategy to overcome this data availability issue within the area of material science or materials engineering. We looked at a few optimal pre-training fine tuning strategies using transfer learning and found ways to create more generalizable models using multi-property pre-training and use that to predict migration barriers which are related to rate performance for battery applications. So, in this lecture we look at diffusion models. These models are mainly used for generative purposes. So, if you want to generate structures within material science, and structure is key to determining it's a key determinant in in estimating any properties that are associated with any application. So, structure is very important in a given material. So, we will try to understand how diffusion models can be used to generate structures. The schematics that I will be using throughout my lecture are from various sources. So, I will indicate the sources in the corresponding slides. Alright. So far we have looked at this conventional sort of materials design strategy, right. So, let us say you have a certain application in mind, you have certain let us say optoelectronic semiconductors, for example, you have certain properties that you need for a material to function well as a semiconductor here. So, what you typically do is to compute properties for a large number of materials, right, and then schematically sort of put them through different filters. So, one filter can be sort of thermodynamic stability, another filter can be band gap, another filter can be excited state properties and so on, right. So, you sort of filter them through progressively more and more difficult to compute properties, and finally you hope to identify a few candidate materials which can be tried out in the lab. So, for experimental validation. So, this is the sort of filtering approach or high throughput approach is what is referred to as conventional materials design. Now, you can also think of inverting this whole materials design problem in this paradigm of inverse materials design, right. So, what we basically want is, so let us say we have a model right that maps properties to structure, and let us say you have some target properties in mind, right. So, you feed these properties in the model and then it comes up with a suitable structure, right, a structure which will exhibit such the properties that you want, right. So, this could be some kind of a machine learning model, right. So, you can say I want a stable material, I want it to be super hard for some mechanical applications or surface applications, and then the sort of model comes up with a few structures, right, a few possible materials. So, this is one area where inverse materials design as a paradigm can be used to identify suitable materials or suitable structures very well. And this is where sort of generative models come into the picture, right. So, you want to have models that will generate suitable structures for any property requirements that you may have, right. So, let us look at how that is done typically, right. So, if you look at generative models in general, so if you look at their the classical way that they actually function. So, the way they work is let us say you have a configuration of parameters, right, or features. So, they basically encode those configurations into a latent space or a feature space, right. So, this configuration, for example, if you take a materials example, right. So, you want to encode some kind of a structure which is a collection of atoms, atomic positions and bonds, right. So, you basically want to encode the structure into a latent or a feature space, right, which can be some kind of a higher dimensional space which represents what the structure is, right. So, what about what kind of information would we want to encode in this latent space? So, composition, right. So, composition plays a huge role in whatever properties that we want. The number of elements and the type of elements play a huge role, right. So, composition is very important. Any structure comes with certain sets of lattice parameters. So, what is the sort of box that you are putting in the atoms, and this box defines your conventional cell, or in the case of defective properties it can also define your supercell, right. So, but the box is important and the box is defined by your lattice parameters. So, your 3 lattice magnitudes and your 3 lattice angles, right. And then within the box you also worry about where the atoms are located. So, atomic positions are very important, right, and it is these 3, right. So, what is the composition, where do the atoms sit, and what is the box, right. So, these are the 3 parameters that you of any structure that you would like to encode in some kind of a higher dimensional space. And one simple way that we can actually encode this information is to actually use our graph networks, right. So we have looked at graph networks quite extensively, right, in the recent few lectures, both in inter-atomic potentials as well as in transfer learning. We have looked at graph networks as a way to intuitively represent any given structure. So any given collection of atoms and collection of bonds into sort of a numerical space, right, into a graph network basically. And once you map a structure into a graph network and do message passing, you can basically get a set of embeddings. Basically that's the set of embeddings that you get is your representation of your structure in your latent space, right. And once you have latent space representation or embeddings for several different structures, you can then map those embeddings to different properties, right. So the step one is what we would like to do. So we want to sort of map a given configuration, so a given structure for example, into a latent space, right, into an embedding space, and this embedding space can then be mapped to properties, right. Second is, okay, so let us say you are given sort of an embedding space, can you get back the structure, right. So this process of getting embeddings from a structure is called encoding. So if you would like to get the structure back from a set of embeddings, then that is called a decoding, right. So we would also like to decode a few, we would also like to decode this embedding space to generate suitable structures or suitable configurations, right. And this is important if you want to create a generative model, right. So let us say we want to put in a certain set of properties, right. We know how properties are mapping onto these embeddings into this latent space. So once we figure out what this latent space should look like for a set of properties that we want, we should then be able to get back the structure, right. So this step is what is referred to as decoding, right, and we would need some kind of models or algorithms that can decode a given latent space. So if you have a latent space, if you have an embedding space, how does that map into a structure, right. This will be noisy, right. So every time you sort of encode information and then when you decode it, so even if it is the same information that you are encoding and decoding, because of the stochastic nature, right, of how these models or algorithms work, there will be some amount of noise. So you may not be able to reproduce or get back the same structure, but if you get a structure that is very close to the original structure that you embedded, the model has done a good job, because you get a structure that is very close to the original and you can do some kind of optimization to make sure that you arrive at the correct structure, right. So basically this process of encoding and decoding, right, basically gives you some kind of a probability distribution, right. So given a mapping between your properties and your embeddings, right, or given a set of embeddings per se, what are the probabilities that these embeddings will correspond to, let us say 2 or 3 different structures. So 2 or 3 different compositions, 2 or 3 different lattice parameters, or 2 or 3 different atomic positions, right. So basically this decoding process gives you a set of probability distributions or the likelihood of, okay, what are the possible structures that you can get given some representation in your embedding space. Okay, so once you build a model that can encode and decode configurations, then the last step is basically using this model for a generative purpose, right. So let us say you have some target properties, you figure out, because you have the mapping between your target properties and your embedding space, you figure out what your embedding space is, what the desired embedding spaces or target embedding spaces, and once you have the target embedding space, then you sample a few structures that are most likely to have that target embedding, right. So you generate a few sampled configurations, right. So the generative models are since they sample some kind of a probability distribution, right, between your embedding space and your configurations and your structures, they will always give rise to a few possible configurations, they will give rise to a few possibilities, and we will have to have some kind of downstream tasks to sort of pick out whichever possibility is most suited for our application, right. So we basically sample some a few configurations that satisfy the embeddings, which are then mapped to whatever target properties we want. And we can also, while sampling, right, while sampling or while generating structures, we can also provide some kind of additional constraints. So we can provide, we can say that we would like a semiconductor with this band gap but also with this composition. So we can give additional constraints that sort of reduces the number of structures that your model will actually generate, which can correspond to a given target embedding, right. So very simply, most generative models, the way they work is you find a way to encode information into some kind of a higher dimensional space, you find a way to decode that information back into your original space, original representation space, and then given a target metric or a target property, you identify what should be your target latent space or higher dimensional spaces, and then you sample a few configurations that should satisfy your target properties, right. So this is briefly or generally how generative models work. So the specific models differ in their own specific ways by which they do encoding, they do the decoding, and they do the sampling, right. Okay, so one of the sort of popular examples of classical generative models is what is referred to as the variational autoencoder. So very simply, this model takes as an input, let us say some kind of a structure or some kind of a representation. It builds a model to encode this information into a higher dimensional space, and then there is a decoder, right, that sort of recovers back whatever structure that you encoded back into the original or very similar to the original structure, right. So this kind of an encoding and decoding process is what is referred to as the variational autoencoder, and there are several examples where variational autoencoders have been used, right. So this is another example where structures along with their latest matrix, site occupancy matrix, and even elemental properties were all put into the encoder, and then you sort of have this property structure high dimensional space where all properties are mapped to high dimensional structural representations, and then you have this decoder to recover back your sort of original representation. So variational autoencoders have been known for quite some time now, and they were one of the first models that were used for a generative purpose, so for generating newer structures. But generative models have gotten through several rounds of advancements, especially in the recent past, right. So as I mentioned in the previous slide, variational autoencoders are the classic sort of generative models that are quite popular in the literature. There are also generative adversarial networks that have become quite popular. These are called GANs, and these are basically you have a generator sort of which generates your latent space, and this generator confuses this discriminator. So the objective of this discriminator is to make sure to identify which is the right representation of your embedding space into your real representation, and vice versa, right. So so the discriminator sort of learns how to do this decoding process, and there are ways that generator and discriminator sort of compete with each other in this generative adversarial networks. These networks became quite popular, especially in the gaming community, but these have been sort of in terms of performance they have been beaten a little bit by diffusion models. We will look at diffusion models more detailed in this in the course of this lecture. But basically the diffusion models try to learn how to denoise a given latent space representation. So it is one way to consider so it's one way to sort of think about decoding a given latent space configuration, but it tries to recover back the original representation through what is referred to as a denoising procedure. We will sort of look at what this denoising procedure is in the subsequent slides, and then there is also autoregressive models that are used for generation, and these are very popular along with sort of language models, and basically they try to predict in sequence, right. So if you have a sentence and if the sentence is partially occupied, then the sort of autoregression model tries to predict the next word, and then once that word is completed, then tries to predict the next word, and so on. So it tries to make a sequential prediction of words that would sort of fit into a coherent sentence given some larger targets. So if you give it a target of write an essay about Indian history or Indian independence movement, for example, then it will try to find words that sort of match the theme, right, and then keep adding words in a sequential manner. So so autoregressive models are more popular among sort of language models in general, not necessarily among graph models. So so we won't discuss very heavily how autoregressive models works, but we will look at how diffusion models work. Okay, So what is diffusion, right? So if you look at the classic definition, basically it's a process that refers to the movement of particles, right, typically from a higher concentration to a lower concentration. So diffusion tries to sort of leads to an equal distribution of particles throughout this system. So let's say you start off with an ordered configuration like this. So you have a high concentration region and a low concentration region. What diffusion tries to do is sort of make these concentrations the same across this boundary here, right. So it moves particles from this region to this region, and then it tries to make the number of particles the same, right. So this ordered configuration is what you can think of as your sort of your initial configuration or your actual representation of your structure. And after diffusion or after disordering your configuration, this can represent your latent space, for example, right. So if you keep adding noise to this ordered configuration, eventually you will get this disordered configuration, right. So if you now learn how to denoise this, so go back from this disordered to the original configuration, then that's basically your diffusion model, right. So let's now look at a simple chain of events that help us understand how diffusion works. So let's say you start off with a clean image, right, something like that looks like this. You keep adding sort of progressively more and more Gaussian noise, so just random noise, right. You keep adding it more and more, eventually you will, all you are going to get is a white noised image, right. So this process is what is referred to as forward diffusion. So you take a clean image and then you keep adding noise in some sort of statistical manner, right. You keep adding noise and then eventually you get a white noise, right. So the reverse diffusion basically tries to reconstruct this whole process, right. So you have forward diffusion that goes from a clear image to a noisy image. In the reverse diffusion, you have a noisy image to start, and then you try to figure out your way back to obtain your clean image, right. So you keep for any given noisy image representation, right, you try to sample which are the probabilistically the most likely ways to denoise that image to get a slightly improved denoised version, and then you keep repeating this process until you get a clean image, right. So this process is what is referred to as reverse diffusion. So typically forward diffusion is what is sort of favored in time, so you can think of this as forward propagation of time. This is basically reverse propagation of time, right, so you are going back in time. And this is a reference to the movie sort of Tenet, where you talk about actually flipping time and going back in time, right. So this is how briefly diffusion models work. So during the training of the model, right, so you show the model your clean image, and then you show the model sequentially how you are getting your noisy image, and with that training process, the model will try to learn how to denoise, right. So how to go from a noisy picture all the way to a clean image. So I will also show you a sort of a GIF image overview of how these diffusion models work. So you see that initially you have a fairly noisy image, and then the model sort of tries to learn and recover back the original picture of this person here. Okay. There are other examples of diffusion as well, especially in image tasks. So let's say you have a spiral, a simple spiral, right, that's your starting image. If you keep adding Gaussian noise, you see that eventually the spiral sort of loses its shape and it sort of becomes very noisy here. In the diffusion model, you try to learn the reverse trajectory. So you start from here and then you try to sample which could be more and more ordered configurations, and then you try to recover back your original configuration. Of course you won't be able to recover back the truly original configuration. There will always be some amount of noise that is actually present, right, in this diffusion process. This drift term, which is represented by mu theta, you can sort of think of mu theta as similar to a chemical potential, but it's actually built into the loss function of your diffusion model. So it tries to minimize the loss as you get back your original shape, get back your spiral. Okay. So how do diffusion models typically work, especially in the image space, right. So you have your image represented as pixels, so that is what is represented by pixel space. It is then converted into a latent space representation through this diffusion process, so you get a final set of embeddings, right. And then there are some conditioning also that you can provide through this diffusion process to make sure that you are sampling the right things basically as you keep adding noise and generating this latent space representation. So when you are now trying to do a generative task, you give it a target sort of metric, and then it tries to go back in this direction. So go back from the latent space representation all the way to a original sort of pixel image or image representation. So diffusion models are actually quite popular in image generation. They usually, the loss is quite low compared to simple variational autoencoders. They are usually stable models in the sense that they generate a representation in the pixel space that looks like an image and not something that looks very noisy, but these are expensive to run. They are about easily 1000 times more expensive than corresponding GANs, right, generative adversarial network. So diffusion models are generally more expensive, but they generally have low loss and they are quite stable in terms of how they run. So diffusion models are actually quite popular both in image and video generation, and these are the models that are powering all of your AI tools that generate videos, images and so on, right. So this is an example of a completely sort of AI generated image here. Okay, so whenever you have sort of a model that works well for images, you can pretty much extend that workflow for structures as well, right, because I mean we saw this example with convolutional networks and graph networks, right, where the process of convolutions sort of translate to the same way as message passing in graphs, and when you do more and more convolutions you sort of learn more and more about the higher dimensional representation of an image. So you go from low level features to higher level features. Same thing with message passing. So you first learn from nearest neighbors and then you go all the way to next nearest neighbors and more advanced long range interactions. So if a model sort of works reasonably well with images, you can sort of expect it to work reasonably well with structures as well, with crystal structures as well. And that is how diffusion models were actually explored within materials for the purpose of structure generation. And one of the first models that actually included diffusion in a simpler sort of variational autoencoder framework is this CDVAE or crystal diffusion variational autoencoder model. So this is one of the first models to be developed for structure prediction, and it uses periodic graph networks basically. So that is the graph networks are used to generate your high dimensional embedding space. And then there is also a property predictor for and that sort of works on predicting compositions, lattice parameters, number of atoms and so on from this latent space, right. And eventually this diffusion model works in a way that it uses Langevin dynamics at the end to generate the final structure. So it starts off with a random structure first and then it employs this Langevin dynamics to reduce noise and it generates a finally sort of ordered structure, and as it samples multiple structures the usual workflow is that you take in multiple of these sample structures and then you determine which is actually the truly good structure, right, for your given application. So diffusion models have been quite popular in the sort of recent literature. So there have been quite a few diffusion models that have been developed by material scientists in the recent past. So this is one example where the authors used diffusion models to design new sort of high temperature superconductors. So you see that they used CDVAE, which is the diffusion model that we sort of saw in the previous slide. So they combine the CDVAE along with Align model. So Align is the model that or Align is the framework, graph network framework that we used for our transfer learning approaches. So they used an Align model to predict your critical temperature, and then they used a combination of these two models to sort of predict newer compositions, newer superconductors, right. A deep sort of the tech companies have also gotten into building diffusion models or building generative models for material science. So for instance Google DeepMind built this diffusion model that was released around the end of 2023, which is basically sort of a structure generator, right. So you give it some kind of a composition or a property and then it tries to generate a structure, and then Matagen is the sort of generative model again based on diffusion that was built by Microsoft, right, and Matagen sort of does a bunch of things. So given as target property it is able to give or sample a set of structures that could satisfy your target property. So the author sort of demonstrated that be it magnetic properties, electronic properties, band gap here, and even bulk modulus. So this is more mechanical properties. Matagen is able to sample distributions way out of what it was exposed during training. So the green bars basically represent labeled data, or training data, and the blue bars basically are the generative data. So even if you do not expose the model to your target properties, it is able to make reasonably good predictions on your target metrics, right. And these are some of the sort of materials that were actually generated, some of the successful cases by Matagen, and they also sort of explored the computational cost. So if you were to generate structures solely based out of sort of DFT calculations compared to using a generative model, the author sort of showed that beyond a certain number of structures generative models can actually sort of make your process much more efficient, right. So Matagen is the state of the art sort of generative model based on diffusion that is available in material science, right. So this is the most advanced architecture out there. The model for a long period of time was not available to the general public, but now you have APIs through which you can access the model and you can actually use it in your own research or other exercises. Okay. So when you come across a diffusion model, right, so there are various things that you have to note or that you have to worry about, especially on deciding which diffusion models are actually useful and which are not. I would say this sort of falls under 4 different categories. One is how valid the structures are when these diffusion models actually generate them. So typically in materials discipline, right, so you do not have structures that have overlapping atoms, right, because when you have atoms that are overlapping with one another, then there is a significant nuclear repulsion, right, electrostatic repulsion between the 2 atoms, that the structure that the atoms will actually explode, right. So there will be almost infinite force of repulsion and they will be forced to move away from one another. So in general you do not come across this scenario of overlapping atoms. So if your diffusion models do predict overlapping atoms, then that model requires further work. And typically diffusion models should always try to predict as simple a structure as possible. See, the point is you can always have a very complicated, very long large structure so with very large lattice parameters, and that is usually not the most optimal solution. So for any given property you would like to have more sort of simpler materials or simpler representation of materials rather than a very large representation. So this is something that one can keep in mind when one uses diffusion models to generate structures. And the other very important thing is whether the structures are charge neutral, right. This is especially true for ionic compounds. So let us say you take the case of sodium chloride for example, right. So if a diffusion model generates a structure, it should for sodium chloride, right, it should have the same number of sodium as that of chlorine, right. Now if you have excess number of sodium, right, then the structure is not charge neutral, there is excess positive charge, right. So one should note especially for ionic compounds whether the generated structures are charge neutral in nature, right. The second important parameter is uniqueness. So how diverse are the generated structures when it is actually sampling your probability distributions. Are the structures basically the same with just minor perturbations of atoms, or are the structures truly very different, so different space groups, different positions of atoms and so on. So in general you would like to have diffusion models that generate a lot of unique structures, because that help you evaluate which structures are actually good for your target application. The third is structure matching, and this is especially good if you have some label data, right. So let us say you already know which is the ground state configuration for a given composition for example, right. Do the diffusion models that you are testing, at least one of them, one of the sample structures that they generate includes this known ground state, right. So let us say you take Matagen for example as a diffusion model, and you have a target composition of let us say sodium chloride, right. So does Matagen may generate 10 different structures, is at least one of those 10 different structures basically the known ground state, which is the rock salt structure for sodium chloride, right. So that is a question that we can ask, especially when we have good amounts of label data, right. So whether the structure that is being generated actually matches with some of the ground states that we know. And the other thing is, especially when we have computational resources such as density function theory based calculations and so on, we can also evaluate how stable the generated configurations are, or how metastable they are, right. So if the generated structures are all very unstable, then the model is not sampling the right probability distribution, but if the generated structures are either stable or metastable, right, then it is sampling the right distributions or distributions that are actually practically relevant, right. So we can think about how stable or metastable the generated configurations are, and typically we have to evaluate this using some kind of underlying physics. So that is either using density function theory or some kind of machine learned heterodynamic potential, a universal potential that works fairly well for the systems that we are interested in, right. So these are the 4 metrics that you can typically use to evaluate diffusion models, especially if you come across several different diffusion models in the literature. One of the examples of diffusion model that we will look at in our hands-on session is Chameleon. So Chameleon actually takes into account both text as well as structural information, right. So each of the text is actually aligned with whatever graph embeddings that you generate for a structure. So for example, if you have LAMN04 structure, there is a graph network based embedding that is generated for that structure, and then that structure is actually matched with this text embedding that corresponds to LAMN04. And the model sort of evaluates the similarity or differences between structures, right. So you see that here LaMNO4 is considered to be quite far away or not very similar compared to a sodium chloride structure, right. So it uses both text as well as structure, and the text is used to sort of guide the denoising process during the diffusion process, right. So whatever target text, target properties or target composition you give, that is used as a guide or as a constraint to make sure that your model predicts structures that are more relevant, right, to your ultimate target or ultimate application. And in principle, if you use a good amount of text data or labeled data, in principle you can eliminate any secondary models such as density function theory or machine learning heterodynamic potential or any other property predictor model, any other transfer learned models for your eventual property prediction. So in other words, you should be able to get the right structure for the right target property in principle, but the way Chameleon has been implemented as of now, this feature has not been rigorously tested or implemented yet, right. But in principle it can be extended to make sure that we do not require additional models to evaluate the structures that are being generated, and we can build in higher degree of confidence in whatever structures we generate, because it uses both because it uses text as a guide during the or a guide or a constraint during the denoising process. So in our hands-on session we will basically be looking at one of the diffusion processes with Chameleon. If this so you see that at time t equals 0, it sort of starts off with basically a black lump. There are no distinct atoms, and then as you keep going through more and more time steps, you see that slowly there is a unit cell that is developing. You see multiple atom types that are generating, and then you will eventually see an ordered structure that is being generated towards the 100th time step. So you see that the structure is evolving slowly, it is denoising. So the grey atoms basically indicate atoms that whose identities are not well established. The green, purple and red atoms are atoms whose identities are established now. So you see that at time step of 64 your structure has become significantly denoised than what it started with. The model also changes the box dimensions. So that also gets changed with time, and you see that slowly it is sort of equilibrating, and you see all of the grey circles are now eliminated. So just nudging the existing atoms in the right direction, and then it has completed its generation process at the 100th time step here, right. So we will try out a simple crystal structure generation process using the Chameleon model in our hands-on session. So with that we will summarize and stop this lecture. So generative models can facilitate structure generation or even some kind of enumeration processes for a given target application or a target property, and these can be used to generate structures that can go beyond simple human intuition, right. So human beings are very good at doing chemical substitutions, for example. So we are very good at working with existing templates and then arriving at newer compositions within the same template, but generative models can be used to arrive at even newer templates, template structures that are sort of beyond simple human intuition. So these models can be quite powerful, and the sort of classical way that generative models were employed is using autoencoders. The more modern cutting edge models use diffusion to sort of denoise your latent space to get a structural representation. And basically diffusion sort of learns probability distributions associated with noising denoising procedures, right. So, it does learn probability distributions as do any other generative models do, right. So, diffusion models can be quite powerful, but they are at the cutting edge and they are susceptible to an extent to generate not so great structures, right. So, if you are interested in using diffusion models, do use them with care, right. So, with that I sort of thank you all for joining today's lecture. In the next lecture we will look at language models and some of their use cases in material science. So, thank you all for joining again.